All right, so 7.7 is on complex numbers. And up until this point in your math career, we've been stuck in the real number system. So this is a very new idea. A complex number is a number where you have some integer plus or minus another integer times I. And the I is the imaginary part, makes it imaginary. So there's the real part, and this is the imaginary part of the expression. And what I is defined as the square root of -1. So up until this point, you couldn't take a square root of a negative. But now you can, because the square root of a negative will just produce an I. It's important to recognize that if you square both sides, so if I square both sides, that will result in I squared being equal to -1. So that is a really, really helpful value when we work with complex numbers. It's important to know that I is the square root of -1 to simplify expressions like this, but it's also important to know that when you square it, you get the -1 so that you can simplify expressions. So for example, the square root of -36, well, that's the same thing as the square root of -1 times 36. And I can take the square root of both of my factors, so I get I and then times 6. And we generally like to put the real part first, so we call it 6I. So then when we have the square root of -50, we can break it up into -1, and we look for a perfect square number that's a factor. So 25 times 2 gives us 50. And I picked 25 because it was a perfect square factor. It was the largest one that goes into 50. And so I get an I from this, I get a 5 from this, and I have a root 2. So I'm going to write it as 5 I root 2. That's the general standard format for it, is the real part, the imaginary, and then the irrational. And the reason for putting the root 2 in the back is just so that it's clear what is or isn't underneath the root, and so things don't accidentally look like they're under or look like they're out when they should be in a different position. So lastly, root 15, we can't simplify. There's no square factors, but because it's negative root 15, we can deal with that negative as an I. So we'd have I root 15. So even though the 15 can't simplify, the negative part can produce an I when you take a square root. So that is the simplifying. Then we'll talk about some other properties with exponents for imaginary numbers. And some of these are just what you'd expect. Anything to the 0 power is 1. Anything to the first power is itself. That's as simplified as it can be. It's just I. We already talked about this one up here. This is really -1 squared. Square root of -1 squared. So it's -1. And then this is I times I times I. And so it's I squared times another I. So it's that -1 times I. So it will get you -I. And then if we multiply by yet another I, or if we read it as 4 I's multiplied together, this is like I squared times I squared. So that will be -1 times -1. It's +1. And if I multiply by another I, it's kind of like this. I go back to I. And then if I do another I, it becomes -1, and then -I, and then 1. And it just has a cycle of 4. So because of that cycle of 4, there's some shortcuts to figuring out what the value would be if we had any exponent where we wouldn't necessarily want to like expand it all out. So there's one way to do it that's more mathematical and formulaic, and then there's like how to basically use your calculator to have a shortcut. So it's a cycle of 4. It just keeps repeating. And so I can say, well, what if I did 4 times an integer, but I have a remainder of 0? That means I'm gone around who knows how many times, but I'm landing with an exponent of 0. Well, that's equivalent to landing at an exponent of 0, which is 1. What if I went around who knows how many times around these 4, and I end up with a remainder of 1? I land there. Well, that's the same thing as I. If the remainder is 2, we get the -1, and if the remainder is 3, we get then -I. So those are your 4 options when you are simplifying with i's to a power. And the trick to this is you could do it like this and say, well, 21 is 4 times what plus what? And you could say, well, 4 times 5, and then I need to add 1. So in other words, you can divide by 4 and see what your remainder is. So in other words, we can see how many times we went through and just care about the remainder. So in other words, I can do the exponent divided by 4. If we get a whole number, meaning no remainder, then we will have 1 as our answer. If we end up with some number 0.25, that means a remainder of 1/4. That's a remainder of 1 out of the 4. Then your answer will be I. And then if you end up with 0.5 when you divide by 4, that's like a half or 2/4. So your remainder being 2 out of the cycle of 4. You get -1. And then lastly, you can end up with 3/4, a remainder of 3. A remainder of 4 would have meant it could go in evenly again, so you'd be back up here. So again, it's that whole cycle. So when I did it this way, and oh, it's 4 times something plus 1, I would end up being able to say, well, this is the same as I to the first, which is I. Or if I took my calculator and did 21 divided by 4, I would end up with 5.25. So there's that 0.25, the 1/4. It goes around 5 times. You'd have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I'm landing there. So again, I'm landing at the I position. So I'll project the others just to discuss them. 43, 4 times 10 plus 3, so it's I to the third, which is -1. I recommend that if you aren't able to kind of reason through what these values simplify to, that you have it as on like a note card to reference. And so if you have remainder of 0, again, anything but 0 is 1. And then I squared, important that you know this anyways. It's important you know that anything but 0 power is 1, that I squared is -1. So the only one that's kind of a little bit trickier is this I to the I to the third, which is -I. And here I have it with the 4 to some power plus what, and then here I have it in terms of what the calculator would give me if I divided by 4 for that trick. You can solve some. This doesn't happen that often. It's definitely not a focus of mine, but when we're doing math, we often like to solve with things. So here's a problem where we could solve for a variable x and y just by recognizing that the real parts have to be equal. So the 3x and the 18 would have to be equal, and then the imaginary parts have to also be equal for the numbers to be equal. So I can then set these equal and solve for x and solve for y. Kind of not a typical problem that we encounter much of. So how do we add and subtract and multiply and divide with I? So 7.7 is got all the operations and all the definitions and all the properties all in one lesson. All right, so basically, you can add the real parts and you can add the coefficients of your imaginary. So you can add your real parts and you can add your imaginary parts. Generically, it looks like that, but it's a lot easier if you just go, okay, I'm going to add my real parts. So I get 5 minus 2, or plus and negative 2 is 3. And then I'm going to add my imaginary parts. So that's 10i. But the formal way of writing it is that you then subtract your real parts and then subtract your imaginary parts. So b minus d I. I'm factoring out the I because I'm just looking at the coefficients of my I. Again, you're subtracting both of these just like you would for polynomials. You distribute the -1, and then you can combine your real parts and you can combine your imaginary parts. So that's adding and subtracting in a nutshell. Multiplying is, again, like polynomials, except there is one thing that you can do that you wouldn't see in polynomials, and that's if you end up with I squared, that can simplify to be -1. So just like we did with polynomials, when we're multiplying a binomial by a binomial, we can FOIL it. So we get AC generically plus ADI plus BCI plus BDI squared. So these two can be combined because they're like terms. And this will end up being, because it's BD times -1, it ends up being negative BD. So you'll end up with two real parts that can be combined. And like we did with regular polynomials with integers as well as with the radicals, now with the imaginary numbers, if we have these conjugates that are, internet's having issues, when you multiply conjugates, you end up with that idea of a difference of squares. And in this case, you'll end up with a times a squared, minus ABI, and then plus ABI or BAI. I'm writing it in the same order just so that it's really clear that these are opposites. And then positive times negative is negative, B times B is B squared, I times I is I squared. Now we have essentially negative B squared times -1. So this will end up being a positive B squared. So we finally actually have a sum of squares. The only time you get a sum of squares is if imaginary numbers are involved. So when we talk about factoring a difference of squares, we never said factor a sum of squares. And that's because generally when we say factor, we are implying it's over the real number system. But this can actually be factored in the imaginary number system like this. All right, so let's just do a couple of examples, and then I'll project a couple as well. So distributing, we end up with 3 times the 5 is 15 times the I, and then 3 times the 2 is 6. I times I is I squared. Because this is -1, we have 6 times -1. So that's going to be -6. So it essentially always changes the sign because it's -1. And so then 15I minus 6. That can't actually be simplified. Is your answer. The next one you do FOIL. So FOIL. I minus 6I minus 14i squared. I often just cross that off and change it to what it's equivalent to, accounting for this -1 times the -14 is +14. So 15 14 is 29. 35i minus 6i is 29i. That was coincidence. They were both 29s. Number 13, I've mentioned a couple times now that when you square, make sure that you write it down twice. So 3 plus 10i times 3 plus 10i. Do not distribute over addition. You must do it twice. You must have an F, O, I, and an L. Okay, so now similarly, I was able to cross this off because it's 100 times -1 is -100. So I did 9 minus 100. And then 30i plus 30i is 60i. I'm putting the real part first and then the imaginary part second. That's called standard form. So it's a good practice to do that. It's a little bit weird though, because I know normally when you see a variable, we put it first, but with imaginary, we always put it second. Here is an example where you have a 2 and a 5i, and a 2 and a 5i, one has a plus, one has a minus, so it's like the difference of squares scenario, but it ends up being a sum of squares when imaginary numbers are involved. So you have that 4 minus the 10i plus the 10i, and then minus 25i squared. And the I squared is -1, so -25 times -1 gives you +25. So now we have 4 and 25 is 29. It gives you a nice integer. When you multiply conjugates, when you have a difference of squares, which with imaginary becomes a sum of squares, but basically when you multiply conjugates, you get a nice integer. And that's going to be helpful on the next section here as well. So here's another one where it's conjugates, and again, you get a nice integer. It ends up being this number squared plus the coefficient squared, because you're always going to have the negative times a positive, but you'll also have the negative from the I squared. So it always ends up being plus the sum of squares type situation. So the reason I wanted to really mention these where you end up with a nice integer is because we don't like having roots in our denominator, nor do we like having i's. We like having our fractions, our rational expressions, be rationalized, meaning that it's a rational number in the denominator, not complex and not irrational, not a square root. So similar to what we did with the square root problems, we are going to multiply by the denominator's conjugate. So you must rationalize the denominator to simplify expressions, and you do that by multiplying by the conjugate of the denominator. Again, rationalizing the denominator is all about the denominator. So I did 3 plus instead of a minus I, so that I end up with a situation where my i's go away and I have a nice constant. On this particular problem, I can divide each of these by 5, each of the coefficients by 5, so I did that to simplify the expression. All right, so we FOILed the top here because it's a binomial times a binomial. FOIL the bottom. Again, these should cancel. I'm just doing it to practice the whole FOIL process, but if you start recognizing, oh, it's going to be 16 plus 9, go for it and just write 16 plus 9 and 25. But if you're still working on the whole process of multiplying and all of that, it might be a good idea just to write it out, especially since you're having to take care of that I squared. These don't all have a common factor, so I can't simplify that. So you could do this kind of like we did with square roots by squaring it. This is a square root of -1 after all, right? So I can just multiply it by itself and just use I and simplify it that way, or I can use the conjugate. So it's like 0 minus I or 0 plus I, and so then I can just have the opposite sign and you'll get the same answer. So there's 2 approaches when you have the monomial. But when you have a binomial, make sure you do the conjugate. So I believe, I'm going to double check, but I believe that is, yep, that is it for 7.7. do you have any questions about any of that overview?
He would try to get in trouble.
No, I don't.
Okay.